James Allen. I'm a data scientist at a consultancy called Sandtable. We work with agent-based models. I'll explain that in a bit more detail in a moment, but essentially it's just computer simulations. And yeah, I'll just describe for you a particular short project that I worked on looking at social inequality, and particularly around the issue of inheriting wealth. So the question that we need to think about here is what happens when you die? Now, I'm not talking philosophically or anything like that, of course. I just mean in a very practical, materialistic sense, what happens to the wealth that you have accrued over your lifetime? And obviously, you choose where this goes. You choose who inherits from you if you write a will. And most people, if they have a surviving partner, will give their wealth or most of it to them, or maybe to their children if they have children. Some people might choose, though, to pass it down further along to lower generations, to their grandchildren or their great-grandchildren, or potentially even further down the line. Obviously, when you're making this decision, the thing that's probably foremost in your mind is how will it affect their lives? How will it affect my children's life if they get an inheritance from me? The question that is understandably not asked as often, but is arguably equally important, is what are the long-term effects on society? Now, this perhaps isn't going to play in so much when you're making your own individual decision, but there are other decisions that need to be taken, such as how should we set up inheritance tax structures, and how can we sort of make things easier for people to make the choice that will produce the sort of more equal or better society, depending on how you want to define better, in the future. And this is the sort of work that was done a lot. You may have heard of the nudge unit, which was a sort of policy unit that was set up under the Blair government, headed by this guy, David Halpern. And he talked about this particular issue of inheritance rules in his book, The Hidden Wealth of Nations. And he made the argument that we should create simple descendants trusts to encourage people to bequeath their assets to their grandchildren and great-grandchildren rather than leaving them to their children. So essentially, you skip out the generation immediately below you in your inheritance and pass it straight down, whatever wealth you have, to the generations underneath them. And he made the argument for this from a social equality point of view. He was saying, even if you are quite wealthy, it's very likely that at least some of your grandchildren and great-grandchildren will have dropped out of your social class. So the idea is that if you encourage people to set up these sorts of trusts, then at least some of the time it's going to benefit people who would otherwise have been quite poor relatively, who will, by virtue of having a relatively wealthy great-grandparent, for example, will then get a lump sum of cash to help them out. Now, you may have seen a similar thing in the news last year. This is Gavin Barwell, who's the housing minister. During the Conservative Party conference, he was talking at an event and described how his own mother had, not through a formal descendants trust, but had done exactly the same thing, in that when she died, instead of leaving her house to Gavin and his brother, she passed it straight down to their children. And Gavin Barwell, despite being the immediate loser in this situation, was talking about this as a positive thing. He was encouraging people to do the same. He was taking a slightly different viewpoint from what David Halpern had been suggesting, in that rather than focusing on equality sort of across people of a given generation, he was pointing out that by passing down to your grandchildren, you're giving them an injection of wealth at an earlier point in their lives where arguably it's more useful to them. And particularly this is often framed in terms of housing, and so he was talking about it being a useful way to get your grandchildren onto the housing ladder. Now, this is not a universally popular idea, and this is the 9th of October. On the 10th of October, the Prime Minister's spokesman made it very clear that Number 10 has no interest in this idea at all, and it's not going to be government policy. It's not something they're interested in doing. Essentially, it's very difficult for politicians to get involved in inheritance tax because it does kick up an awful lot of emotions. It's something that's very difficult to make progress on. But the idea hasn't gone away. And in fact, there was a report just a couple of weeks ago from Royal London, the insurance company, this was based on a fairly large survey of people from 3 different generations who are in the sort of different stages of expecting to pass on an inheritance or receive an inheritance, or maybe get skipped out of an inheritance and see it go straight down to the children. What they found in this survey was that actually, even if you say in your will that all of my wealth will go to my children, or if you don't write a will, and so that sort of happens as the default option, that doesn't necessarily mean that that's what your descendants are going to do. And what they found is that when looking at baby boomers, and this was specifically essentially people who are expecting to receive a housing-based inheritance from their parents in the not-too-distant future, the majority of these people said that they expect to pass some or all of this inheritance straight on to the next generation. But they did point out also the sort of major flaw in this idea, if you want to talk about it in terms of social equality. Well, the numbers they gave, that only around 4 million of the 17 million people in the 25 to 44 age group are in the fortunate position of having grandparents with housing wealth. Now, obviously, housing wealth is not the only sort of wealth, even though this is how the conversation is normally framed. But it does point out the very significant point that whatever sort of inheritance system you set up, it's clearly going to be most beneficial for the descendants of rich people. And so you might throw up your hands and say, well, there's no point in exploring this at all. We're clearly not going to solve all of the problems of society by doing this, and that's absolutely true. But I think it's still valid to ask the question, well, if we tweaked inheritance tax laws, or if we made it a little bit easier to set up the descendants' trusts that David Halpern was arguing for, what will be the long-term effects on society? It's clearly not going to be a universal solution for everything, but will it make things perhaps just a little bit better in the long run? Okay, so this is where the agent-based models come in. This is where we can test it out. Now, this video is just sort of a conceptual picture of what an agent-based model is. The basic idea is that it is a computer simulation of some sort of complex system. And the specific point of an agent-based model, as opposed to other sorts of models, is that it works from the micro-level behavior, and from that works out what the macro-level results will be. So instead of trying to go from the top down of, say, predicting what the economy is going to look like in 10 years, straight from the top-level figures, you would look at, well, how do people spend money and earn money, and how does finance move things around, and just play that out, and then from that see, okay, what are the top-line numbers that we're most interested in. So in this particular example, it's just different colored circles, and each of these circles is one agent, and they're each following a set of rules that defines their behavior. Now, the agents in an agent-based model can be anything, really. In what I'll be talking about today, they are individuals, but they could equally, in other circumstances, be households. They could be entire corporations or countries. If you sort of extend the definition of an agent-based model a little bit, then you could talk about individual agents being galaxies or being molecules, anything where you can sort of define a set of rules that govern their behavior, then you can essentially make an agent-based model out of it. So as I've been saying, you need to give your agents a set of behavioral rules. If you can't write down what those rules are, you can't build a model. And often there's going to be some sort of set of assumptions that go into that. But that's how it goes. You also will typically give your agents an environment to interact with, which could cover all sorts of different things, but will often include the other agents themselves. And that's how you can get things like sort of flocking behavior or something like that, where the actions of one agent depend very strongly on the actions of the agents that are around it. Now, once you've set up your behavioral rules and the environment, and you've sort of got your agents ready to go, then you pretty much just press play and see what happens and measure whatever results it is that you're interested in. Okay, so if we want to build out an agent-based model of the inheritance system, then we need to think first about, well, what data do we need to gather in order to make this feasible? Well, there are a couple of obvious ones to start with. We need to know what the birth rate and the death rate are so that we get sort of the right numbers of people going through the population. We need to know what I've called here the coupling rate. Now, if this was a very sort of traditional Victorian society, then we could just look up the marriage rate and that would be okay. In the 21st century, about 50% of children are born to married parents and 50% unmarried parents. And so we need to know, for the married parents, it's very easy to find out what the rate of marriage is. Every marriage in this country is recorded, and we can just look that up. For the unmarried parents, obviously, we know a lot less about how often people form long-term relationships. But we do know a lot about the birth rate to both married and unmarried mothers. And so we can, if we, for the purposes of this model, just sort of define coupling to be forming a relationship that has the same fertility rate as marriage on average, then we can simply sort of take the marriage rate, compare it to the birth rate, and just sort of extrapolate out the marriage rate to get the right number of couples being formed in the model. As far as the model is concerned, we don't care if they're actually married or not. Now, as well as coupling, we need to know about uncoupling. Not all relationships last forever. And this becomes important in the model because if you have children with one partner, but then split up, then you may go and have more children with a second partner. And obviously that plays into how your wealth gets spread around after you die. So that sort of defines the really raw demographic data of just how many people do you have and how they relate to each other. We also need to know about the distribution of wealth, very obviously, and also the distribution of incomes. If we're going to play the simulation out over a long period of time, then it's not just your wealth now that is important, it's how this plays out over decades or 100 years. Another useful piece of information is the connection between income and education, which unsurprisingly is quite strong. Now, there are a lot of other things that income depends on, but education is a particularly important one for this model because there is a very strong relationship between parents and children's education. If your parents went to university, you are much more likely to go to university than someone whose parents didn't. And so, even putting everything else aside, and these 2 points immediately mean that you have quite a strong correlation between your parents' income and your own income, just through having similar levels of education. Now, the great thing about living in the UK is that, as mentioned particularly by the full fact people earlier, almost all of this information is available from the Office for National Statistics, the ONS. They really are a fantastic resource. I cannot recommend them highly enough. If you're building any sort of models of this sort, if you ever need to set up a representative population of the UK, then you'll almost certainly be able to find what you need on their website. And it's just free to search and download. Okay, so that kind of defines the sort of bits of data that will be going into the model. We also need to write down what our set of behavioral rules will be. Now, the way ABMs typically work is we talk about a tick loop. This is just a for loop that's going round, and each cycle of the loop is a fixed amount of time that we call a tick, just the same as a clock ticking onwards. Now, your choice of tick size depends entirely on what you're trying to model. But in this case, a year is a fairly suitable choice. It's the sort of timescales that you're interested in terms of families and birth and death and inheritance. Okay, so what happens within this tick loop? Well, each time you go around, your agents all grow older. All of the adults in this simulation earn money, and they save or invest 5% of that income. Now, obviously, this is horribly simplistic. Real people's finances are much more complex than this. It's also kind of very optimistic in that everyone has an income, everyone is able to put away some of it. I should sort of just explain this 5% saving and investing. This isn't just what you can put into a bank account. If you've got, if you have a mortgage and are paying into that, then that is effectively an investment as well, because you're paying into your housing wealth in that way. So yeah, as I was saying, this is a very simple model, and for sort of future improvements of the model, this is probably the first place that I'd go to try and get a bit more of a realistic look at how people really earn money. But this should do for our purposes of just having a sort of simple idea of how people might, on average, earn money in order to test out the different types of inheritance, which is what we're really interested in. Okay, so another sort of simple and optimistic bit is that all adults in the model earn 3% interest on their wealth. And again, this is not just your actual interest on your savings account. This includes increases in property value as well if you own property. And again, this is simple. This is averaging over the fact that some people do have property that's going up in value, some people do not, and so their effective interest rate should be a lot lower. But we don't want to do a full housing simulation for this particular purpose, so we'll just leave it at that average for now. Okay, so if your agent at this particular tick is single, then they have a chance of forming a couple. And I'll come back later to some of the details of that, but essentially you just look for people who are kind of similar to you in age and wealth, and then in every year you have some chance of forming a relationship with them. Okay, but then also, as I said, if you're in a couple, there's a chance of splitting up. And as I was saying before, these things vary. The exact details of the probabilities here are very strongly informed by the ONS data that we have. Again, also, if you're in a couple, then you have a chance of having a baby in any 1 year. For the sake of simplicity, there are no twins or triplets or anything in this model. You can only have one baby a year, as far as I'm concerned. So then, when you get towards the later part of your life, when the agents hit the age of 65, then they retire, and half of their wealth just sort of disappears. Now, what's happening here is that wealth is going into an annuity. Now, this is just when you sort of pay out a lump sum, and then that is what guarantees your income for the rest of your life. So you know that you're not going to run out of money, that you've got some, you have guaranteed income. But as far as your inheritance is concerned, then that money is no longer accessible to you. Now, if you die at the age of 66, then you've kind of lost out because you've put all this money away and then it just disappears. But you do it because if you instead happen to live to the age of 100, then you still have that income throughout the rest of your life. Okay, but also in the model we say that once you have retired, you're not earning anymore, and you just sort of gradually run down your savings. You're living a bit off that as well as what's coming out of your annuity. And then, of course, the really crucial thing for this model is that all agents have a chance of dying in any given year. And again, this is entirely driven by the ONS data on death rates at different ages for men and women. Okay, so then comes the bit that we're actually sort of interested in testing out, these different inheritance rules. So there are two base options, essentially. We have kind of the default, that is what most people are doing now, which is that if you have a partner who is alive, then you give all of your money to them. If your partner has predeceased you, or if you split up, then your wealth is split between your children. The other option is, again, if you have a surviving partner, then the money goes to them first. But otherwise, instead of going to your children, the money gets put into a descendants trust, the thing that David Halpern was arguing for. And this descendants trust is for your grandchildren and great-grandchildren in the sort of default setup we put into the model. And the way it works is that sort of that money is there, it's accumulating interest while it's in this trust. And when the beneficiaries reach the age of 18, then they get their fair share of the money that's in there. If they're already 18 or over when you die, then they get that money immediately. And to compare these two different options, we just run the model twice. We run it once where everyone takes option 1, and we run it once where everyone takes option 2, and we compare the results of the two. Now, obviously, this is kind of unrealistic in that we're saying that either 60 million people make one decision or 60 million people make the other decision. But we do this just to give us the largest possible baseline to compare the results and produce the largest effect possible to see really what we're interested in here is the effect positive or negative. Okay, so in terms of actually building this in Python, I'm not going to show you any code or anything. If you're interested in having a look, then there's a GitHub repository that has the model code and the raw data in it as well. But just as a brief description, and this kind of describes most of the models we build at Sandtable, we use the familiar open source packages that most of you will know from your day-to-day work as well. We pandas a lot, particularly for the sort of initial data ingestion and processing. The simulation itself is mostly built in NumPy. We can represent ABMs very simply using NumPy by just assigning each variable of interest to an array. So for example, the age of all of our agents is an integer array of length, the number of agents. The wealth of our agents is a floating-point array of length, the number of agents. And because we're able to write down what the behavioral rules are, well, it's very easy to turn that then into a few lines of NumPy code that manipulate those arrays within each tick. SciPy comes in normally just when we need sparse matrices, which, if for this particular model, was useful for keeping track of who is related to who. But then one of the things about ABMs, and one of the reasons they've not been used too much until quite recently, is that they're very noisy. There's a lot of random choices that are being made at every step along the way. And what this means is that to get any useful results out of it, you really have to run the thing hundreds or maybe thousands of times and aggregate your results up, take some sort of average. And so, to do that, suddenly it doesn't really become feasible to run on my laptop. And so we turn to AWS for that. And I've really got to give a massive amount of credit to the dev team at Sandtable, who've put together some wonderful services so that I, as a data scientist, don't really have to worry about what's happening there. I can just say, give me a cluster with 200 cores and run my model 1,000 times, and it happens, and the results come back, and I'm a happy data scientist. OK, so let's look at some actual results then. And the nice thing about ABMs is that you don't just have to look at the top-level picture, which is what sort of most models will tell you. You can drill right down and look at what is an individual in my model doing. This is really interesting from a curiosity point of view, and it's also a massively useful sort of sanity check on everything you're doing. You need to, if you look at the individual level results and people are doing weird, stupid things that make no sense, then you know there's a problem that you need to go and fix. OK, so let's look at the life history of one of the agents from the model. I've called her Mary. And this is the version of the model where you have direct inheritance, where people pass their wealth down to their children. Now, so this is it was starting in 2016 and running outwards. Mary was born in, that's about 2030. Yeah, we'll look at the sort of the vertical lines first. What we're seeing is that at the age of about 22, she formed a couple with someone. They had 3 children over the next few years. Unfortunately, they separated when she was age 40. She didn't form any further relationships after that. And she lived until she was in her late 70s. This is now into the 22nd century. Now, this blue line is tracking her wealth over this period. And what we find is that she sort of starts off with nothing. She's working. She earns throughout her lifetime. This is where she retires and puts half of that into an annuity. And then when she's aged about 70, she inherits quite a large amount from her parents, who the second of her parents has just passed away. But she only actually lives a few years longer than that, so it doesn't actually make a massive amount of difference to her in that sense. If instead we switch over to the version of the model with these descendants trusts, this agent that I've called Paul, he was born a few years before Mary. He formed a relationship at a similar age to her in his early 20s. He actually has 5 children, and he stays with that same partner for the rest of his life until he dies in his 80s. But what we can see here is that if we look at his wealth, we have 3 separate distinguishable jumps where he has inherited some wealth from his grandparents or great-grandparents. And obviously this is happening at a much earlier time of his life than it did for Mary. So although they each actually inherit a similar amount in their lives, and they actually earn reasonably similar numbers as well, I think it's perhaps slightly higher for Paul. But if I flick between the two, you can see that really at all times in his life, Paul is the wealthier of the two, because he's had this injection of wealth at an earlier time in his life. Okay, but that's just sort of 2 individuals. We really care about the population level results. So to look at this, we use a measure called the Gini coefficient. Some of you may have worked with this value before, but essentially what you do is you line up your entire population ordered by how much wealth they have. And then you take the cumulative sum along that ordering. Now, if everyone in your population had exactly the same amount of wealth, then you would plot this straight line curve that the cumulative fraction of wealth is directly equal to the cumulative population fraction. And that corresponds to a Gini coefficient of 0. That is the least unequal society you can have. If there is some distribution of wealth, then the first people will contribute a smaller amount to the cumulative fraction, and so you get a curve that drops below this equality line. And the Gini coefficient is actually mathematically equal to twice this shaded area. So this is for a fraction of 0.48. If we had a more unequal society, then that goes up to 0.75 in this example. If you had the extreme case where one person has all of the wealth and everybody else has nothing, then you get a line that just comes straight along the bottom and then goes up to the top, and that's a Gini coefficient of 1. Okay, so what does this actually look like? Well, we've got a 150-year simulation run 2 times, and this is plotting the projected Gini coefficient for the entire adult population. And what we see is that these intergenerational trusts or descendants trusts, they do really make a significant difference, that at a population level, you have a less unequal society as measured by the Gini coefficient if you bring these things into play. But that was kind of obvious because, as Gavin Powell pointed out, you're giving money to people who are at an early stage of their life, who typically have less wealth than older people. So the next question is then, well, within that population, are you just entrenching the inequality that's already there, or are you helping out? So if we look down just at the people sort of aged 20 to 39, then although these lines have narrowed a bit, there is still a significant difference that the people in the simulation with the intergenerational trusts, even if you're just looking at one generation, because we have this effect of spreading your wealth amongst more people, then you do get a less unequal society, one with a lower Gini coefficient. Okay, so there is some bad news. It doesn't all work out well. One thing that kind of confused me when I first saw this was that descendants trusts actually increase the correlation between your and your parents' wealth. Even though they've reduced inequality, they've increased this correlation. It took me a while to work out why this is happening, but essentially it's because you're often drawing from the same trusts. If your great-grandparents make a descendant's trusts, then your parents, their grandchildren, will inherit from it, and you will inherit from it. So you actually are getting sort of the same pot of cash to draw from. So once you notice that, then it's not surprising that we get this increased correlation. And indeed, you can make the effect go away if your trusts pay out only to one generation. So if you make it only for your grandchildren. There's also an issue around what's called assortative mating. So this is the effect that people tend to form relationships with people who are similar to themselves. Now, similar can mean a lot of different things. Obviously, in this case, we're thinking about wealth and income. And so there is a parameter in the model that defines sort of how important is that to people. How likely are they to match up with someone who has very similar wealth to them, or how likely are they to just pick someone essentially at random? And so we can tune this parameter and see what the different outcomes are. The dashed line is what I was showing before, and I should say this is just among the young people in this particular plot. So the dashed line is what we believe to be roughly the strength of assortative mating in the real world. If you take it away, then the descendants trusts have a stronger effect. If you increase the assortative mating, they have a weaker effect. So there is this relationship here. But even in this strong case where the strength of assortative mating is twice what we believe it to be in the real world, then there is still a difference that lasts for at least 100 years in that the descendants trusts have improved the situation as far as inequality is concerned. Okay, so just to wrap up and give you the takeaway messages, the sort of social takeaway here is that descendants trusts would overall decrease inequality. And they do this in two ways. Firstly, by transferring wealth to younger people who on average have less at the moment, and also by spreading wealth around even within a generation. There is a slight caveat in that they may increase the correlation between your and your parents' wealth, and that sort of unfairness may be an important factor in deciding what to do about these. And also sort of the strength of assortative mating, and I have no idea what the predictions are for how assortative mating will be in the future, but it is an important effect on how well the trusts work. But then the sort of technical take-home from this is that all of these sorts of things, and many more besides, can be explored using agent-based models. They're a really great tool set for this sort of exploratory work, particularly for complex interacting systems. Okay, so I'll just put up my contact details, and there was the GitHub repository where you can take a look at the model, you can play around with the parameters, play around with the rules, and I'd love to see if anyone comes up with some new conclusions from the model. Okay, thank you.
Fantastic, thanks, James. Questions?
Yeah, could you talk about performance? Like how many agents, how long did you run it for, and so on, or what the parameters were?
Yes, so this was done using an initial population of 10,000 agents. Now, obviously, that changes over time as people are born and die. And so on a single core, then to get the 150 years, that takes, I think, about a minute or something like that. So the limiting factor in the current implementation is in the coupling system. What it does at the moment, because in terms of fertility, it's the woman who's sort of more important in defining whether there will be a child in the relationship, then we sort of choose a fraction of women who will form couples in any 1 year, and then compare them to all of the eligible men. And that comparison is quite slow, and particularly as your population grows, then obviously it kind of blows up a bit. With a better implementation of that sort of system, where you're a bit smarter about which men you're comparing to the women, then I think you could improve the performance quite a lot.
How do you deal with volatility of people's earnings? I mean, if you're looking at the ONS statistics, it would be easy to assume that the top 1% was the same set of people year after year. But maybe it's people who are selling businesses with massive temporary increases in their income.
Yeah, and that's a very good point, and it's one that's not really dealt with in the model. As it stands, the only change that we have in there is that as you grow older, your earning potential increases. And that's pretty easy to pull out from the ONS data. It would be very interesting to look into those sort of issues of volatility, both in terms of income and in terms of wealth, as well. But yeah, it's not something we've had time to do yet.
Sorry, mine is just more of a general question on ABMs. How do you manage to input so much data, so many varying parameters, and still keeping the output simple enough so you can extract insight from it?
Yeah.
I know it's a challenge.
It is a challenge. This model, it was actually relatively easy to do that because it's really the more data, well, the more useful data you have, the easier it is to do this, in that we can simply look at the ONS data for deaths, for example, and say, okay, if you are a male aged 63, you have an X% chance of dying each year. And so that just goes straight in. We sort of don't have to worry about it, really. It's a well-defined rule. The difficulties come with ABMs where you don't know your information so well. Now, I work a lot in commercial applications where you want to know what the probability of someone choosing a particular product is, for example, and that's much less constrained. So in those sorts of situations, you have to look at what data you do have. You look at a lot at survey data and other sort of monitoring data, and find different ways to match the model up against the reality. Because in this model, we only had actually one tunable parameter, which is the assortative mating. In a commercial model, there might be very many parameters, and we've got to find sort of different pieces of information to calibrate each of those against.
So would you say that assortative mating, that's a parameter that's agent-agent interaction, right?
Yeah.
But what about agent-environment interactions? How do you model those in these cases?
So in this case, it really was the sort of fairly simplistic income. So income and education are the main things there in terms of interaction with the environment. And this model has a very simple implementation of those. It is literally just the rules that I put up there translated into NumPy code. So as pointed out, there's a lot more that could be done there. But yeah, it's just a matter of how much we have time to investigate and really trying to focus on the things that are important to the inheritance bits.